Okay, this is a video on ion formation and how to draw ionic bonding through electron configuration. So what we're first going to take a look at is really what ion formation is about. So an ion, if you remember, is a charged particle where you can have a cation, which is positively charged, or you can have an anion, which is negatively charged. We talked a little bit about this when we were doing the trends, and we talked about ionization energy and electron affinity, and that they would be forming ions. But what I want to do with you is I really want to talk about how ions can be formed. So the first element that I'm going to ask you to consider is the lithium ion. And if we were to look at the lithium ion kind of in an old Bohr type model, there would be 3 protons in lithium, and there would be 3 electrons in a cloud around, or in these rings around lithium. I'm also going to ask you to consider what lithium would look like in electron configuration. So up here, if we were to write the electron configuration for lithium, it would be 1s2 and 2s1. So 2 electrons are in the first ring, the first orbital. 1 electron is in that second orbital, and that would represent the valence electron. There's 1 valence electron in lithium. So in ion formation, lithium will really want to get rid of this 1 electron. So I'm going to kind of just move it over here off to the side, and that can go and get transferred somewhere. And lithium now will have 3 protons still in the nucleus, but now around the nucleus are only 2 electrons. So there is an overall +1 charge left over in the lithium ion. We no longer call this a lithium atom. It's called a lithium ion because it lost that 1 electron. So if we were to write lithium as an ion, we put a plus there, or you could put a +1 there, indicating it lost 1 electron. What would its electron configuration be? 1s2. So what we're representing here is that this valence electron was released, okay? It was gone. It gets transferred maybe to something else, but that has been transferred, that 1 electron. Now what's significant about this is that the lithium ion now has an electron configuration of 1s2, which is the same electron configuration for helium. Helium has an electron configuration of 1s2. So it's stable electronically like the noble gas. Let's take a look at another element. We're going to take a look at beryllium. And if we were to consider beryllium's electron configuration, it's 1s2, 2s2. There's 4 protons in beryllium. There's 4 electrons in beryllium. You'll notice that the 2s2 represents the 2 valence electrons. They're in the second quantum level. There's 2 of them. They are the 2 valence electrons. So if these 2 valence electrons were to leave, so I'm just going to get them out of the area. Okay, so we're going to just move them off to the side. They get transferred. Beryllium now has 4 protons in the nucleus, and it has 2 electrons. So the overall charge of the beryllium ion is +2. And we would write beryllium ion as a +2 charge. Its electron configuration is 1s2, the same as the noble gas helium. So these are how cations are formed. There is that tendency for them want to give away electrons or transfer electrons, okay? Let's take another look at a bigger molecule. This is fluorine, okay? Another ion formation could be on the anion side. And if we write the electron configuration for fluorine, it's 1s2, 2s2, 2p5. This indicates that there are 7 valence electrons for fluorine. I've got 9 protons here being represented with the blue positives. I've got some neutrons in there. I also have 9 electrons here depicting a model of the fluorine atom. Now, would it be possible for fluorine to donate or to lose all 7 of those valence electrons? And the answer is no. What's going to happen is that an electron is going to be transferred into fluorine. So now, here an electron is getting transferred into fluorine, and its electron configuration then is going to be 1s2, 2s2, 2p6, showing that electron that's been transferred in. And if we count this up, fluorine has 9 protons, but now it has 10 electrons. So there is an overall -1 charge on this atom. It is no longer the fluorine atom. It is called the fluorine ion, and we write that with a -1 charge. Okay? What about oxygen? Let's take a look at oxygen. Oxygen has 8 protons. Here it's got 8 electrons around that nucleus. Oxygen's electron configuration is 1s2, 2s2, 2p4. What happens is that oxygen will have the tendency to gain 2 electrons. So when it gains 2 electrons, it now has, let's see, oxygen would have 8 protons, but it has 10 electrons around the outer shell. That means it's got a -2 charge. There's 2 more electrons than there are protons. Oxygen's electron configuration then is 2p6. This indicates the 2 electrons that were gained, and we no longer have an oxygen atom. We call it the oxide ion, or the oxygen ion. Okay, and that's what happens in ion formation. So there is a loss or gain of electrons in order to reach that noble gas electron configuration because it's more stable. All right, moving on then, we can write electron bond or ionic bonding through electron configurations. Again, elements are going to want to transfer electrons or gain electrons in order to get stable like the noble gases, okay? The first example that I'm going to show you is sodium chloride. I wrote out, and this is what I'd expect you to do if we were asking you to write ionic bonding showing electron through electron configuration. You would write sodium's electron configuration, which is 1s2, 2s2, 2p6, 3s1. Notice there's 1 valence electron. That's the 3s1 electron. Then you write chlorine's electron configuration, 1s2, 2s2, 2p6, 3s2, 3p5. Now, if sodium was to transfer this 1 electron to chlorine, sodium then now has the electron configuration like a noble gas, and chlorine has the electron configuration of a noble gas. And that's all you have to show for ionic bonding with electron configurations. You write the electron configurations, and then you show an arrow that shows the transfer of 1 electron. It's also important to note here, notice that sodium has, the sodium chloride is in a bonding in a 1-to-1 ratio. There's 1 sodium for every 1 chloride. This happens because of the electronic structure, okay? You would never see NaCl2 because that just doesn't work with the way these electron configurations are, right? Another example here is calcium and oxygen, okay? Calcium's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. 2 valence electrons in that s orbital in the 4th quantum number. Oxygen is 1s2, 2s2, 2p4. Calcium would transfer 2 electrons to, so I'm drawing 2 arrows, to that 2p4 orbital. Calcium now has the electron configuration of stable argon, ending in 3p6, and oxygen will have the electron configuration of neon, okay? Notice that calcium oxide combines in a 1-to-1 ratio. That's because electronically, it's 2 electrons are lost by calcium, 2 electrons are gained by oxygen. Finally, we're going to take a look at aluminum chloride. Now with aluminum chloride, the electron configuration for aluminum is 1s2, 2s2, 2p6, 3s2, 3p1. There are 3 valence electrons. So those 3 valence electrons in aluminum will be given up. But chlorine, if you notice, these are the electron configurations. I should write this. These are the electron configurations for chlorine, which is 1s2, 2s2, 2p6, 3s2, 3p5. And what happens is that you need 3 chlorines to account for the 3 electrons that aluminum has to transfer. So that is why the ratio for aluminum chloride is AlCl3. It's all based on the electronic structure, okay? This is a table, and this is in your book. This just talks more about the formation of the ions, which is what we were talking about here. But this is a great table, and you should really, in class, I had students, put this down on their periodic table. The first group with lithium, sodium, potassium, rubidium, and cesium, they all make a +1 ion. Group 2 all makes a +2 ion. When you look at group 3, aluminum will make a +3 ion. The one that we didn't have on here is that nitrogen, I have to write nitrogen, it's just N. N can make a -3 ion and its whole family. Oxygen will make a -2 ion and its whole family. And of course the halogens, they all have a -1 ion. And this will help you. You'll notice that these are what we call the S. So these are the S block elements, and these are the P block elements. And you can tell that it's pretty easy to determine the ion that it would form based on the group that it's in. Okay? Finally, the last thing we talked about in class today was the relative size of some ions and their parent atoms. Lithium is larger than the lithium ion, and that is because the lithium will lose that 1 electron, and so then the lithium ion becomes smaller. Conversely, fluorine atom is smaller than the fluorine ion. It's gaining an electron, so it becomes bigger. The trend for this, and here's another picture that's just showing the ions. This is showing lithium, beryllium, and then they get really small till you get to carbon, and then you'll notice it gets big again with the nitrogen, the oxygen, and the fluorine in that picture. And here I've got on the left here, I've kind of got the trend that it decreases until you get to carbon, and then at nitrogen it will increase again, and then it will decrease. So that is the trend for ionic size. It's different and not as clear-cut as atomic size. So that is it for this video. Hopefully you've learned something about ion formation, and you also can draw ionic bonding through electron configuration. Good luck.